Set.
How's it going, guys? This is Rich with Wolverine Airsoft, and today on What the Tech, we're going to be taking a look at the brand new Phoenix Hop from Wolverine Airsoft. So since we launched the MTW about 2 years ago now, people have been asking for a CNC version of the hop-up for the MTW. Up until now, I haven't done one, and that largely comes down to the fact that I don't like to put products out unless we can do something that is really different, that we really believe in the value of, that performs and functions differently, offers a different value to customers out there. The Phoenix Hop does just that, and we're going to get into why. To start off with, if we just look at this thing, it obviously looks very similar in exterior design to the existing stock hop-up. Now, the obvious differences are that the body is CNC aluminum, it is anodized, and it has this strange little slot over here on the side, which we'll get to. And it looks a little bit different at the back end, but it shares the same basic components. So your C-clip here, and your adjustment dial and hop-up arm, all those parts are backwards compatible, which is nice. So, what is the big difference here? Because I've been hyping this up, I really believe in the product, and I want to explain this to you. So, it's no secret that one of the key performance variables with a hop-up system is the amount of force that it requires to load the BB into the hop-up chamber to push past the bucking lips. This variable is what we'll call bucking lip tension, right? It's the amount of force that it takes to load the BB into the chamber. Now, this is an important variable because it impacts a ton of things. It impacts your sealing. That will also affect how tight the seal is between the bucking lips and the front of the nozzle. It can affect the consistency of the hop-up. It can affect whether the system jams or double feeds. There are a ton of different variables. Now, it's also no secret that in general, HPA systems are more sensitive to this than AEGs. And there's a ton of variation within HPA systems, how sensitive they are. Something like the Gen 2 Inferno is much less sensitive than a pure open bolt system, but they all tend to be more sensitive than their AEG counterparts, and I'm going to talk to you about why. All right, so let's for a moment set aside the loading mechanics of an HPA system, because they vary widely. A true open bolt system is going to load it and fire it all in one motion. A sort of hybrid system like the Gen 2 Inferno, there's going to be a very slight pause between the loading and the firing. The Reaper or other closed bolt systems, the BB will load and then sit there and then fire. So that varies, but we know across the board, regardless of the loading mechanism, that all HPA systems tend to be more sensitive to this. So it's not exclusively the loading. The loading does complicate this. And you can go back and look at some of the videos we did early on with the SMP, which is a true open bolt system, talking about how to deal with some of these issues. But it's not exclusively the loading. It's also the firing. So let's take a look at just the firing sequence. So here we have our BB loaded in the chamber. This is our hop-up bucking. The nub sits right there. And then our nozzle is sitting up against the bucking lips, sealed, ready to fire. This is the same. Everything we've shown so far is the same, regardless of whether you're talking about an AEG or an HPA system. What's different is the firing mechanism. So, with an AEG, you have a pressure wave that looks something like this. Let's draw a graph. Let's get nerdy for a second here. Here's time. Here's pressure. Okay? Because you have a spring compressing a piston, which then compresses air to fire the BB, it takes time for that pressure to build because the piston needs time to move forward and build pressure, and it needs more time, so the pressure waves look something like this. Not exact. You're actually going to have a sharp drop-off once the BB leaves the barrel as all the pressure vents, but we care about this front part because at some point we're going to call here the BB experiences first movement. That means that the BB overcomes the resistance of the nub and starts to move. So we see that leading up to this, it's a gradual slope, and then it moves past the nub smoothly. Now, let's talk about what happens with a HPA system. And this is true regardless of what HPA system. Instead of having a spring and piston, you now have a valve, which can either be open or closed. And I'm going to draw an electrical valve because I don't feel like drawing or an electrical switch because I don't feel like drawing a mechanical valve here. But you get the idea. Here's our nozzle. Once this closes and air is allowed to flow directly through, the pressure builds very quickly. Okay? This is our first movement line. You can see the pressure builds much faster behind the BB with any sort of HPA system, regardless of how the BB was loaded. So, what does that mean? How does that play back into the sensitivity to the force required to load the BB? Well, what that means is that any small deviation in the position of the BB with respect to the nub is going to be amplified, right? Because if you get just a little bit wedged past the nub, maybe not fully past the nub, but you're just a little bit wedged under it because you loaded the BB a little too hard, or there wasn't enough resistance, or you're sitting back, or you haven't quite fully loaded it yet, or anything like that, is going to be amplified because this pressure builds so fast and it gets accelerated past the nub more quickly. Now, the obvious question, if we know that you need the right amount of resistance to loading the BB, or the amount of force on the system loading the BB, why don't we just pick the right amount of force with the system when we design it, with the engine, let's say, when we design it, so that it always loads properly? Well, here's where we get into the million variations within airsoft manufacturing. No two combinations of rubber and housing are going to create exactly the same resistance to loading. And it's not that there is one exact right amount of loading force. It's that the loading force needs to properly match the amount of resistance. So you can be off either way, right? If you don't have enough loading force, well, now the BB's not going to load and you're going to run into issues, or it's not going to load quickly enough. Or if you have too much, then you're going to run into issues. So because of the manufacturing tolerances and the different dimensions of the hop-up rubbers and the hop-up housings that we have to deal with, you can't have an exact right amount of loading force. Now, we can design the systems so that it is less sensitive to that, right? So Gen 2 Inferno, really good example of this. Much, much less sensitive than earlier systems and some of the other systems on the market to the amount of loading force. Even with a system like the Gen 2 Reaper, where the amount of loading force is exactly the same every single time, regardless of operating conditions, if you get outside the envelope of acceptable resistance, you're going to run into issues like double feeding or jamming or just general poor performance, again, because of the fast firing cycle. So with that as a background, let's talk about what we actually did with the Phoenix Hop, okay? This is a really cool and simple solution to this. What we wanted to create was something that lets us precisely control the amount of loading force needed so that we can precisely adjust it and tune it. This will make the hop-up housing work well with a far broader range of hop-up buckings and other variables, barrels, things like that. The barrel, the hop-up bucking, all these things have an impact on how tight that interface is. So we wanted to come up with a system where we could precisely adjust what we're calling the bucking lip tension, or the amount of loading force. So let's talk about how that works. Inside the hop-up, what you have, I'm going to draw this here so that you can see it. We're going to draw a cross-section. So here we have what we call the adjustment screw, threaded. Here we have the adjustment sleeve, which has an internal taper on the front end. and has an opening at the bottom that lines up with the feed tube. So this is where BBs load up. This is cross-sectional area here, just so we can see what's going on. Then you have your hop-up rubber. And your hop-up rubber, the lips of the hop-up rubber sit right here like this. And then inside, you have the nub. So you can see the tapered portion of the hop-up sits inside this tapered portion of the adjustment sleeve. Now what that lets us do is, you can see, if you look at the back of the hop-up here, you have the threaded insert that we show right there. And if we take this little tool that comes included and we turn the threads, we're going to push this taper more or less up against the hop-up rubber, which is going to compress or allow the hop-up rubber to expand. So what that lets us do is it lets us precisely control the amount of force required to load the BB into the chamber. Really, really simple. So let's take a look at this, put this together, and show you how it works in practice. This is just like any other of our hop-up housings. If we remove the adjustment wheel at the back, we'll see we have this O-ring back here, which is our friction O-ring. We want to note that there is a small polyurethane pad underneath this O-ring that keeps friction on this adjustment screw so that it doesn't back out or back in, either way. As you're playing, it doesn't move, it stays put. And it also provides a nice amount of friction on the wheel so that it moves smoothly, but does have some friction there and will not move while you are playing. The hop-up arm is our standard arm. We tested some different designs and found that this worked just as well as anything else, and so we're sticking with that design. So let's go ahead and put this together. I have a Maple Leaf 70-degree bucking here. I'm going to go ahead and install the bucking. You will, as usual when you're doing this, you're going to want to put a little bit of silicone lubricant on the hop-up rubber. We've already done that here, so I'm just going to go ahead and install it. And then you're going to line up the barrel correctly so that your barrel window is facing to the top of the hop-up, and then you're going to snap your C-clip in place and wiggle that around and make sure it's seated correctly. Now, I picked the Maple Leaf specifically for this example because it's a really good example, because by itself there is not enough resistance to keep the BB from simply falling through. You can see if we set that there and just slightly tap it, it just falls straight through. There's almost no resistance. The lips on this hop-up rubber are very thin, so they don't provide much resistance to loading the BB. But watch what happens as we adjust this. Tighten this down a little bit, and you can see, I'll do this sideways so that you can see this here. You should be able to see on the video, through this window you can see the sleeve moving forward and back as I adjust it, and that's adjusting that tension. So we're going to set it right about there and see how it does. Now when I drop it in, definitely not falling through. So I'll try pushing it through. That's actually about where I would like it. A little bit of force required to load it through, but not too much. You can see if you continue adjusting it, you can eventually make it much too tight, which you don't want to do, and then it will require a great deal of force if you can even get the BB to load at all. In this case, the BB doesn't even want to load. So let's go ahead and set it back about where we want it. So let's go ahead and finish assembling the hop-up here. Obviously you have your nub of your choice that will sit in the arm. Make sure it stays in the arm as you're putting the arm in place. And then you're going to put your wheel on. Now the wheel, you're going to want to start on the side with that little insert on it because it sticks out a little bit. You're going to want to kind of hook that side, pop it on, and then pop the wheel in place. The last piece to install is going to be the tapered locking ring, which slides on the front and fits snugly inside to keep your barrel aligned with your hop-up. Now let's talk about one of the other really cool benefits that came out of this, which is that by having an internal sleeve, remember we have this internal sleeve in here, and an external body that are two different pieces, it lets us make them out of different materials. Now, those of you that have listened to some of the stuff I've said in the past know that I generally like polymer for hop-ups. Now, the reason is that while the stiffness of aluminum is nice and has some benefits in terms of the consistency, the lower coefficient of friction of polymers improves feeding and consistency on full auto and things like that. So what this lets us do is it lets us get the stiffness of the aluminum while using a very low friction material for the sleeve inside. So the internal sleeve is actually Delrin. It's a self-lubricating polymer. So it lets us have the stiffness with the very low friction qualities of a polymer in the areas that we're actually sliding. So this acts as a bushing inside where the nozzle is sliding, because one of the things that we know happens is that the force, let's draw what's happening inside here. Here's your nozzle, here's your BB, your stack of BBs coming up from the magazine, and here's your hop-up. Now, the force from the spring in the magazine is pushing on the bottom of this nozzle and causing it to make contact with the top surface of the hop-up housing. Right? Now, that rubbing usually doesn't cause an issue per se, but when you're running high rate of fire and you have two materials like both of these being aluminum that produces a decent amount of friction, it can cause some inconsistencies. Again, especially on full auto, you'll see maybe things seat a little differently and it catches a little bit because it's dragging. So having a very low friction interface here between the nozzle, the top of the nozzle, and the top of the hop-up housing gives us better feeding and better consistency, especially with full auto. So that's about it for this episode. It's already been a long episode. I apologize for that, and we didn't want to drag it out anymore. So we're going to throw a separate discussion of the application of some of this to R and flat hops in a appendix after the closeout of this video. So if you are into R hops or J hops or S hops or whatever else, stick around. We'll talk about why some of this is particularly relevant for tuning those types of hop-up systems. So to wrap this up, let's take a look at the list of what the benefits are for the patent-pending technology in the Phoenix hop-up. First of all, you get improved feeding, increased durability and reduced wear, a superior air seal, improved groupings with a broad range of barrel and hop-up setups, and superior full auto performance. Currently, we only have the Phoenix Hop available for the MTW. We do have plans to introduce it for other platforms, so stay tuned for that. So if you stuck around for the bonus R-Hop section, props to you. Let's talk about why this has, to some extent, changed my perspective a little bit on R-Hops. Why are R-Hops particularly sensitive to this? Now, let's draw a picture of an R-Hop versus a standard hop-up. So, to illustrate why this adjustable bucking lip tension is particularly relevant to R-Hops, S-Hops, flat hops, things like that, I've drawn out a cross-section here of an R-Hop and a traditional hop-up rubber. So an R-Hop, well, first let's start with the traditional. The traditional has an opening in the barrel window, and you have this distinct mound that protrudes down into the barrel, and that is what puts backspin on the BB. It catches the BB and spins it, right? An R-Hop, the patch is built into the window, and even when engaged, it only extends very, very slightly into the cross-section of the barrel. Now, this is one of the reasons it can work well. It engages gradually. It's also one of the reasons it's extremely durable, right? Because you don't have an edge to kind of catch on and the BB to kind of tear up the rubber over time. But think about this from a loading standpoint. Even a small mismatch, let's take a small mismatch in the loading force with the traditional. And you have this distinct edge that the BB, when it comes in, is going to bump up against. Right? It's going to hit that and it's going to stop. Right? Now, if your loading force was a little excessive or your tension on the bucking lips was a little low, you're still going to hit that, you're still going to stop. It's probably not going to have a huge impact, right? It's going to be kind of minor, right? Because it stopped, it still has to kind of push that nub up and out of the way, and it's going to get the majority of the backspin applied. With the R-hop, a very small mismatch in the loading force to the resistance is going to result in different placement here. It's going to push it further forward or further back underneath the patch. And because the R-hop doesn't depend on an edge to catch it and then spin it, it depends on continued acceleration with gradual engagement. So it's this real gradual engagement, but it stays in contact for longer. Well, by that force not being a perfect match, you're pushing it a little bit too far forward, and then things like variations in, you can have variations with this in terms of how empty is the magazine. Okay, one of the cool things that this Phoenix Hop has let us find is some of the weird things that have shown up over the years, things that people have talked about with, and that we've seen with what people call mid-cap syndrome, right, where the system hops differently with a loaded magazine and an empty magazine. It comes back to stuff like this, right, because if you have very little resistance here, what's going to happen is that the nozzle is going to see different amounts of resistance from the force in the magazine depending on how compressed the spring in the magazine is. So it's going to place this differently up against that patch, right? It can happen in extremes cases with a traditional rubber, but it's much less common. We've been able to, and we can recreate if we want to. We can recreate mid-cap syndrome by setting the tension mismatched to the feeding force. All right, so it really has expanded our understanding and let us made these things recreatable so that we can adjust things and figure out what's actually going on and how to solve it and make the performance better. So this mismatched loading force is particularly relevant to R-hop. Again, just a final review here before I wrap this up. Because there isn't a distinct stopping point. It doesn't load the BB and then kind of have a stopping point that then it accelerates off of. It gets pushed in and then there's just this real gradual slope, and if it got pushed in a little too hard, it might go a little way down that slope and kind of stick. And then if it catches on the nozzle catches a little bit on the next BB as it's trying to load and doesn't push it quite as hard or quite as fast, now it falls back a little bit. So that's where the resistance of the bucking comes in to normalize that so that you get a consistent loading force every time, or a consistent loading speed every time that is matched to the force of the system that you are using. And I can tell you from my personal experience, I make no claims of being an R-hop expert in terms of actually installing them, right? There are people that have much more experience than I do with that, and I'm happy to defer to them in terms of the specific processes for exactly how they do it. But I will tell you that my success rate with making R-hops has dramatically improved by using this hop-up chamber versus previously it was very hit or miss. One would work and then several wouldn't, and it wasn't very predictable exactly why some installations went better than others. Very consistent results in terms of how the total installation performs with this Phoenix hop-up technology.